All right, so we've talked about moment of inertia for objects that are rotating around a certain point. But for example, if we have a ball rolling, actually, let's do a hula hoop. Let's say you want to spin a hula hoop. So this is my hula hoop. And I want to spin it around such that it kind of rotates just like this, and it's rotating around the middle. Well, if it's a hoop, that means that it's going to have a moment of inertia of mr squared. And it would be pretty easy if I had a way of rotating this around to make it rotate like that. But if I wanted to then rotate my hula hoop around a point, say on the side, like around right here, and then have the hula hoop rotate so it's here, and then it would be like this, and then it would be like this, and it would be rotating around in a circle. And so if it was rotating around in a circle kind of like this, where it's moving around and around, but it's rotating around this one point here that's not in the middle of that circle, then this moment of inertia is not going to be mr squared anymore. And so, in fact, the way to figure it out with regardless of what shape it is you are going to add mr squared to whatever the moment of inertia is before. So in this case, my radius is r, and then this moment of inertia is just mr squared, or when I rotate around the middle. If I rotate around the edge of this circle, now I have this distance that I'm going to add to it. So it's going to be whatever my moment of inertia was before. So in this case, I would equal mr squared. And then I would have to add to it this new distance, which also happens to be r. So this would be plus the mass again. But now it's times this new r, because that's how far it's rotating around. So it's nice when it's a circle. This could also be like a ball. So here I have a bowling ball, and I'm going to have my bowling ball rotate. And you'll notice it's rotating around the bottom because the top is not where it's rotating around. It's not moving at that point at the bottom wherever it's touching the ground. So that means that my point that I need to rotate around then is down here. So I'm going to have to do this plus mr squared thing to it. Now for this one, it would be a bowling ball. And a solid bowling ball has a moment of inertia of 2/5 mr squared. You don't need to care why. And then if that bowling ball is rolling, now we have to add to it mr squared, because between the middle of the bowling ball and where it's rolling also has a radius of r, and so that's where I get this plus mr squared in blue. It's just because it's not rotating around the center of the bowling ball. So then this whole thing is going to be my new moment of inertia, and I'll just call that moment of inertia rolling. And then you'll also see that the notation that Mr. Clark uses is I with a CM here to notate that this is your center of mass. So when it's rotating around the center of mass, or what I like to call the middle, that's when that hoop is going to have a center of mass, or a moment of inertia of mr squared. All right, this also would apply to weird shapes. So like if I had a ball here and a ball here and a ball here, we did a problem kind of like this before. Maybe we have it spinning around a point right here. Let's just say it's something really weird, and it would be rotating around this way. I could say, whatever that moment of inertia was of this whole thing. And then I could be like, hey, let's say now I've figured out what that moment of inertia is around this point, and now I want to rotate it around this point right there. Then I could use this as that r. And so whatever my old moment of inertia was from the whole thing, I could then go plus mr squared, where this is the distance from the new place I from the old place I was rotating it to the new place I'm rotating it. And then I'm able to figure that out without doing all the math all over again. Hope that's helpful.